Hello, everyone, and welcome to today's reading group.
Today, we have torsional diffusion for molecular conformation generation, covered by Gabriele Corso and Bowen Jing. And if you want to join this reading group sessions yourself in the future, find all of the information in the description.
Me and Bowen are the first author of this work. We are both PhD students at MIT. Bowen is advised by Tommy Jacola and Bodenberger. I'm advised by Tommy Jacola and Regina Barzilay. And so this is joint work with Jeffrey, who is a PhD student at the Department of Physics at Harvard, and Tommy and Regina, which are as us at MIT.
I advocate for saying Bowen and me instead of me and Bowen. Sorry about that.
Okay, so today we're going to be talking about torsional diffusion for molecular conformer generation. Before we start, let me just say a couple of words. So we dedicate this work and this presentation to Octavian, who's a dear colleague, a great mentor, an amazing friend, without whom this work would have never been possible. Unfortunately, he passed away a couple of weeks ago, and is such an incredible loss for the whole field. And he will be dearly missed by everyone that met him. Okay, to go into our work, so we are dealing with the task of molecular conformer generation. So we start, we're given a molecule, so a molecular graph, and we want to find the set or configuration that the molecule can take in 3D space. And these are typically called conformers. And this is a critical task for drug and catalyst discovery, because many of the properties that the molecule has and the way that it interacts with other molecules and proteins depend on the 3D structure of the molecule. Now, there are two classes of traditional methods, the so-called DFT and metadynamics, which are where the idea is basically that you try to understand the energy landscape of the molecule, and then you try to find the conformations that minimize this energy. However, the problem with this is that they are typically too slow. They are very accurate, but too slow. So for example, for an average drug-like molecule, if running DFT takes about a couple of days on CPU. So as you can imagine, if you're scanning for like millions of molecules, this is far too slow. So there have been many cheminformatics methods developed, which try to do this with rule-based and knowledge-based methods much faster. However, the problem with this is that they are still too inaccurate for many applications. Recently, machine learning methods have been developed, but they are also kind of limited to approximately the same performance of these state-of-the-art cheminformatics methods, as we will see. So one of these machine learning methods, and the one that is most closely related to our work, is that of Euclidean diffusion models. So diffusion generative models have been very successful over the past couple of years for image generation. The way that they work is that, for example, for an image, you start from a set of images and in your pixel grid, and to every pixel you add Gaussian noise. And so you add increasing amount of Gaussian noise until your pixel basically becomes, your image basically becomes a randomly sampled vector. And so you train a model to reverse this this process of adding noise. And so then at inference time, you can start with a random vector and gradually sample an image. So at the last ICLR, there was a work from Minka Xu et al. Called GeoDiff, which tries to do the same for conformer generation. So they add Gaussian noise to each atom coordinate, and they obtain results competitive with machine learning and cheminformatics state-of-the-art methods. But one of the problems is that it takes 5,000 inference steps to sample each conformer, which makes this method's orders of magnitude lower than the methods it performs similarly to. Okay, so the idea behind our work is that we can actually, with some observation of molecular flexibility, we can actually significantly reduce the space over which we do the diffusion, and therefore significantly improving the runtime and the performance of these diffusion models. So the observation is the following, is that the molecular flexibility actually lies in the space of torsion angles. And local structures, which are, for example, bond length and bond angles, can actually be predicted very accurately by cheminformatics methods, because if, I guess if you study some chemistry, you typically know that if you have a covalent bond, these are typically have a specific length. And if you have, like, for every atom, the bonds tend to take particular angles. And so these are relatively simple to predict by these cheminformatics methods. On the other hand, the torsion angles, which kind of like determine the overall shape of the molecule, are much harder to be predicted because they are much more flexible. And you can see here in this image, let me see if I can get a pointer. So here we are showing kind of the effect of rotating two of the torsion angles of this molecule. So the one over this bond, which creates this effect, and this bond, which creates this effect instead. And so, as I mentioned, the idea is that we restrict the diffusion process to these torsion angles of rotatable bonds. And this significantly reduces the average dimension over the space over which we operate for a drug-like molecule, which has on average 44 atoms. And so we start in the Euclidean diffusion, you have a space of free n dimension, which is 132 dimensions, to less than 8, which is the number of rotatable bonds.
So, like, because instead of having 44 atoms whose location we're changing, we now just have 8 rotatable bonds that we're changing.
Yes, pretty much. So you have to look at the space over which you operate. So when you have 44 atoms, the space over which you are operating, which is by changing these atoms, is 132 dimensional. And when you instead kind of like are perturbing the rotatable bonds, this space, obviously, it's a very different space, because as Bowen is going to introduce, is actually not an Euclidean space, but it's a space of only 7.8 dimensions on average.
Don?
And can I ask a question?
Of course.
So you're assuming here you know the bond structure, right? You're not starting from just the chemical elements.
So we are, I'm not sure I completely got the question. If I understand correctly, you ask if we assume that we know the local structure.
The bonding structure.
Yeah, so we assume we don't know it, but we take it from RDKit, for example,
okay.
Other methods.
And then,
sorry, could I? Sorry. Oh.
Yeah.
Yeah, sorry. I think the question was whether or not we're doing molecular generation versus conformer generation, whether or not we know the bond graph. So we're assuming the setting of conformer generation, where the bond graph is given to us as part of the problem, and the task is to generate the conformers of that specific molecular graph.
Thanks. And then, sorry, just another question. Do you have like some numbers? You say the torsional angles are much more flexible and have much higher variability and are harder to predict than bonds and angles. Like, can you quantify that a little bit? Like, how much harder is it? Just to sort of get a little bit of a ballpark.
Yeah, it's a great question. So the problem is that it's a bit hard to quantify. And for example, in our paper, we have some histograms of the error done by this by RDKit, for example, on predicting bond length and bond angles. Another way that you can quantify it is by looking at the minimum distance that you can get from, for example, if you get a conformer from RDKit, and what's the minimum distance you can get from the ground truth to the ground truth conformers if you rotate the torsion angles. And so this is something very similar to something that we do in the paper, and we report some results. And to give you an idea, this is about 0.25, you get over to a RMSD of about 0.25, 0.3 Armstrong, compared to the 0.9 Armstrong that is the current performance of current methods. So yes,
awesome. Thank you.
It's not perfect, but it's much better than, like, if you take RDKit, the main issue, you can get a long way by just working on the space of torsion angles.
Wait, so if I take the RDKit conformers, say for all of geom drugs, and I change the torsion angles as good as possible, then what would be the...
Yeah, so we actually have some results in the paper. And so if you take a random RDKit conformer and so this is our table 5 in the paper. Unfortunately, I don't think, let me see, maybe I have it in the supplementary material. I can show it later. But if you take a random RDKit and a random ground truth conformer, the RMSD between the two is 1.5 Armstrong. And the matched RMSD, so if you change the torsion angles to be as close as possible, is about 0.3738. And you can reduce this by, instead of looking at the random conformer and a random RDKit conformer, to actually match them, so that is actually, because if you actually look at the distribution, not to specific ones.
Okay, so the original RDKit conformer, or the average RDKit conformer RMSD is 1.5, and the average RMSD kit conformer with corrected torsion angles is 0.3.
Yeah, more or less, yes.
So 5 times lower RMSD.
Yes, to some extent, but this is also like not a great measure, because you're not looking for, first of all, it's obviously an approximation because you're doing some differential evolution, and also these numbers that I'm quoting do not match conformers, but basically the bottom line is kind of the same. Yes.
Nice.
Yeah, just to add an intuition, like these numbers that you're giving, 1.5 angstrom, 0.2 angstrom, like the diameter of the hydrogen atom is about 0.5 angstrom. So when you're saying that you're about 0.2 or 0.3 difference without the bond angles, it's really like smaller than a hydrogen atom, which is the smallest possible atom, and the error is quite so the error is like very small and very accurate in that case. Whether when you're talking about an RMSD of 1.5 angstrom at the beginning, then here it's like stacking 3 hydrogen atoms on top of each other, and this is the average error that you would get.
I mean, Gabriele, maybe you can point out how much an angstrom is, like, about in your figure here.
Yeah, I'm not. I wouldn't. It would be speculation, so I won't try to do it.
But it's like one bond here, right? Like one of the bonds in this drawing.
Yeah, carbon hydrogen bond is roughly 1 angstrom, like 1.1 or so.
Okay.
Okay. Thanks.
Thank you.
What do you mean by the 7.9 rotatable bonds?
So I mean that if you, so we are evaluating these over a data set that we're going to introduce later, which is, as you know, 300,000 drug-like molecules. And we are calculating that on average over these drug-like molecules, there are 7.9 rotatable bonds. And Bowen is going to introduce a bit more what a rotatable bonding is, but you can think of basically.
You can look at the figure.
Yeah, you can look at the figure at basically any of the bonds that are rotating, but is any bond that is not in any cycle and is not at the edge. Maybe Bowen is going to introduce it a bit more carefully.
All right.
Okay, so with this, I'm gonna give the floor to Bowen, who's gonna introduce the method.
Sure. Okay, thanks. So to get into a little bit over the formulation of torsional diffusion, we first recognize that the distinguishing property of the Euclidean diffusion approach that we talked about earlier is that it views conformers in terms of extrinsic coordinates. And by this, we mean that in that framework, you consider a conformer to be a point cloud in 3D space, parameterized up to some global rototranslation. So if you do this, it's pretty hard to disentangle the degrees of freedom that are hard to determine from those that are easier to determine. And so for torsional diffusion, we take an alternate approach of viewing a conformer in terms of its intrinsic coordinates as a tuple of the local structures L and the torsion angles tau. So to give a little bit more detail about what these are, the local structures L includes the degrees of freedom that correspond to bond lengths, bond angles, and the conformations of cycles, including the torsion angles within cycles. And these we are regarding as local structures because these will be the degrees of freedom that we will explicitly label as being quote unquote easy to predict and things that we will not try to predict with our model. Instead, our model will focus on the remaining degrees of freedom, which is the torsion angles around rotatable bonds. And as Gabriele alluded to a little bit earlier, by rotatable bond, we specifically mean those bonds such that if you sever them, you have two connected components, which each have two or more atoms. And so importantly, this does not include bonds in cycles. And the reason for this is simultaneously a logistical issue and also a chemical issue. Chemically speaking, most of the cycles in our data set are pretty small, and especially for aromatic rings, for example, the torsion angles about those are pretty well determined already. So we can group them with the bond lengths and angles as things as being easy to predict. The more logistical issue is that you cannot independently define arbitrary perturbations to torsion angles in cycles. And so for simplicity's sake, and also to further reduce the dimensionality of the space, we focus solely on the torsion angles around a specific set of bonds. So once we have defined the space of conformers as being this Cartesian product of the space of L and the space of tau, what we then say is we're going to have a generative model that learns only the conditional distribution of tau given some local structure L, as shown in the bottom line right there. And we are going to use an existing cheminformatics method. Specifically, we're going to use RDKit, the ETKDG routine in RDKit, to predict all of our local structures, and then use our model to refine, if you will, or generate the torsion angles conditioned on that local structure. Next slide, please. So the tricky thing about having defined a conformer in terms of these intrinsic coordinates is that the torsion angles don't define a Euclidean space, right? Since the torsion angle ranges from 0 to 2 pi, and 2 pi is the same as 0, the space of m torsion angles is a hypertorus, which we're going to label as Tm throughout these slides. So how do we do diffusion modeling on a non-Euclidean space such as this? Well, in the score-based diffusion modeling framework of Yang Song et al., which was also extended to general compact manifolds by De Bertolli et al., all we need in order to define a diffusion model on the torus is a way of sampling from the heat kernel on the torus and a way of calculating the score of the heat kernel. So for the torus, this is actually pretty easy because the torus has the nice property that it's the quotient space of Rm, regular Euclidean space. And so the perturbation kernel on this space is just the wrapping of the heat kernel on Euclidean space. And so essentially the score of this kernel just becomes an infinite sum that you can pre-compute and just store on disk. On the right-hand side, we're trying to show a little bit a visualization of how distributions on the torus map to distributions in conformational space. So here we're introducing two different views of the diffusion process, which we will later elaborate on greatly. One of these is the intrinsic view, where we are looking at the space defined by the torsion angles, which, as I've described, is the torus, and you can see the evolution of a heat kernel on the torus. In the extrinsic view, we recognize that this toroidal space does not exist in isolation, but every point on the space maps to a conformer. And so a diffusion on the torus maps very naturally to a diffusion over conformers in 3D space, where the perturbations of increasing magnitude are applied to each of the rotatable bonds, only two of which are shown here for simplicity. So one additional property that is important to note is that the uniform prior, the prior that the diffusion converges to on the torus is no longer a Gaussian. Since the manifold is compact, it converges to a uniform distribution. And so when we sample from the prior of the diffusion model, we'll actually be sampling uniformly over the torus, which can be easily done by drawing a random torsion angle and applying it to the conformer.
So in the end, you say that the diffusion is just for every torsion angle we draw uniformly from 0 to 2 pi.
Yes, that's correct.
All right, Don?
Yeah, and you're saying if you have, like the torus that you're showing here, you have two torsion angles where the rotation of one angle is equivalent to rotating that way, and the rotation of the other angle is rotating that way, right?
Yes, that's correct.
Yeah, and if you have 5 torsion angles, then you're going to look at a 5D torus.
That's correct.
Okay,
that's correct.
Perfect. Thank you. That's a nice visual for something that that's actually complex.
Next slide. Okay, so now that we have defined a diffusion process on the torus and have a handle of the ingredients that we need, the next step is to figure out how we're going to develop our score model. So first we note the input and output spaces. The output space needs to be the tangent space of any point on the torus. And luckily, that's just the normal Euclidean space Rm. So that part is pretty easy. The harder part is the input to the torsional score model. So since we're doing intrinsic coordinates, you could think we could just provide the model with the intrinsic coordinate parameterization of a conformer. However, this has a couple of problems. First of all, the dimensionality of this toroidal space, it obviously depends on the number of rotatable bonds. And furthermore, even for molecules with the same number of torsional bonds, for different molecules, or even for the same molecule, the meaning of a given point on the torus, that is the mapping from points on the torus to actual conformers, is not well defined. One of the reasons for this is that it's hard to parameterize the local structures L, and we don't have a visualization showing this right now, but essentially what's going on is that you have degrees of freedom in L that are constrained, and it's hard to have a non-arbitrary parameterization of the manifold that satisfies those constraints. That's the issue with parameterizing L and feeding it to the score model. An additional issue arises with tau as well. And the reason for this is that the torsion angle at a particular bond, which we have been referring to with impunity so far, is actually a little bit of a problematic notion, because a torsion angle, strictly speaking, is a dihedral angle, which requires a choice of 4 points. And essentially what this means is that to define a torsion angle, to actually have a numerical value for the torsion angle that you can provide to your score model, you need to choose a neighbor for each of the two bonds, each of the two bonded atoms for the bond that you're considering.
And like if we say we have 3 neighbors for each, maybe we can take Gabri's toys, right? Is it good in my camera as well? Or should I go with Gabri's camera? Yeah, anyway, like if we have our rotatable bond here, maybe, then why can't we just average over the neighboring atoms, and then we end up maybe with a vector here and a vector here, right? And then we can take those as our four points between which we define the dihedral angle.
Sure. Yeah, so there are definitely ways that you could work around this to have a canonical definition. So one of the issues that could arise from what you propose is that if you have symmetries, then sometimes you will have essentially a degenerate case where it will no longer be possible to define the angle. Like for example, in the case that you described, if the three are located equidistant and equally equiangular as well, then the 4 points will actually be collinear and you will no longer have a dihedral angle. With that said, there are other workarounds that avoid these symmetry issues. For example, Octavian's paper in Geomol, he developed a way of parameterizing a torsion angle for an arbitrary bond without choosing neighbors. But in order to make that happen, he had to train a neural network that would essentially compute weights for the different neighbors in order to choose that canonical point. So while there are workarounds, it is a little bit of an issue that injects a little bit of ugliness into the formulation. And so what we wanted to do in this work is see if there's a way around that where we don't have to come up with these hacks, as it were. If you're further interested, definitely read Octavian's paper. He goes into much more detail about choosing a choice of tau in there. So our approach is instead to recognize that we don't necessarily have to have a score model that takes in intrinsic coordinates. All we want is a model that outputs a score on the space of intrinsic coordinates. So that's why we introduce a framework that we call an extrinsic-to-intrinsic score model, which, as the name suggests, is a model that takes in a extrinsic or Euclidean formulation of the conformer, that is its position of each of its atoms in 3D space, and predicts a SE3 invariant score for each rotatable bond. And so the way that this works is you have a scalar prediction at each bond in the 3D point cloud, which you can easily construct using well-developed equivariant point cloud-based networks, which we'll talk about briefly in a moment. And you just treat those M scalar outputs as the components of your torsional score on the torus, which is in the tangent space of the torus. So that's just Rm. So the output space matches, and the input space, there's a little bit of a workaround, but it enables us to not have to worry about any of the issues in the first 3 bullet points. In particular, and this is maybe the focus of this parameterization or this approach, is that we no longer have to choose a choice of neighbors at all, because even though we're working on the torus, and you might say, oh, well, you need to know your location on the torus at any point in time, right? Even if you're not feeding the torus to the score model, you need to have a notion of the diffusion on the torus, which is not well defined if you don't have a position on the torus. Well, this also is something that we don't have to worry about, because if you look at the score-based modeling framework, you're always dealing with changes, displacements on the torus, which we are labeling as delta tau. So at no point in time do you actually need to have a value for tau at any torsion angle, at any rotatable bond. You always work with delta tau. And with this parameterization, if you fix the local structures, which we are doing, the change in any of the possible choices of the torsion angle is always the same.
Okay, so like my understanding is, because you just predict a change of torsion angle, it does not matter how you define the torsion angle. Like you later on, when you go ahead and apply your change of torsion angle, you can choose any of the possible torsion angles by choosing any of the possible bonds and just apply the change. It won't matter which which bonds you chose to define your torsion angle.
It's true, but even more interestingly, you actually don't know to define any of them. So we actually in our model never make any of this choice, because you can directly apply on the 3D by just rotating one half of the molecule around that bond. So we actually never make any parameterization, even if it wouldn't matter of the torsion angle.
Okay.
Yeah, and it's worth noting this is only true if the local structures are fixed. If the local structures are not fixed, then this is no longer possible. But luckily, we're in a setting where the local structures are in fact fixed.
Oh, good. But maybe also it's helpful just to very briefly say, like, as a quick summary of the whole stuff that we're doing, right? We have the space of torsion angles, or we have a molecule with some rotatable bonds. The rotatable bonds have torsion angles associated with them. And now in your diffusion model, you can diffuse the torsion angles by adding a little noise to them, and then we end up with some messed up conformer. Yeah, and your model now learns to reverse this diffusion and always predicts a little tau, a little torsion angle change to reverse the diffusion. And then if we start with random torsion angles, then we can go from them to good torsion angles, because your model has learned to predict the changes it needs to make to those bad torsion angles.
Yes, that's right. Great summary.
All right, let's go.
I have a quick question. Do you learn a diffusion model per configuration, or do you learn a diffusion model that has an input configuration, so it's general for any configuration?
Oh yes, so the model is it's specific to the data set. So yes, it generalizes across all of the different molecules in that data set. So in our case, we do drug-like molecules, and there's 300,000 of them. And the way that this is done, and the reason that it's possible, is because we're using these 3D point cloud-based ecovariant networks, which can be, those are essentially GNN-like. So of course they generalize to, or at least we train them to be generalized across, all of the possible molecular graphs from the distribution in our data set.
So the local structure is like a subgraph for you, I suppose.
Oh, I see. So the local structure is, you can think of it as a constraint on the 3D point cloud. So yes, what we train on is we try to sample the distribution of local structures that we would get at inference time, which is the set of local structures, the distribution of local structures that we get from RDKit. And you have actually anticipated a major point that Gabriele will talk about in a little bit, which is a distributional shift between the local structures in the ground truth and the local structures that we have access to during inference time. Since we want to train on what we test on, we have to train on local structures that are generated by RDKit rather than the local structures from the ground truth. And so there's a little bit of a distribution, a domain shift adaptation issue that we address later.
Thank you.
Next slide. Okay, great. So as has been presented in the previous slide, our score model takes the form of a SE3 invariant point cloud-based network that predicts a scalar for each rotatable bond. However, there is an additional symmetry that we have to take into consideration, which is that the underlying energy is parity invariant, or as you can also say reflection invariant, right? Two mirror images of the same molecular graph with the same local structure will have almost exactly the same energy. The asterisk is there because it's a very interesting physics fun fact that there is a small difference that you can read more about, and someone got a Nobel Prize for it once. So it's actually very interesting, but for sake of brevity, we won't talk about that too much more.
No, I mean, at the very end of the presentation, I think you have to spend a few words on that. I have no clue what this is about. Okay.
Oh, okay, sure. Yeah, all right, maybe we'll do that. Anyways, so the implication for our work is that since the distribution is parity invariant, the score actually needs to be parity equivariant. And so it's not sufficient to just predict a normal scalar for each of the rotatable bonds as the torsional score. That actually won't work. We actually have to predict something that's SE3 invariant and parity equivariant, which people in the physics literature will affectionately know as a pseudoscalar. So on the right-hand side, we kind of illustrate on the right bottom side. Sorry, I can't really point to it, but yeah, thank you. You can sort of see visually why this is the case. If you imagine that the energy is the same for two mirror images of any molecule, if you focus on any of those bonds, you can see that if you want to predict a clockwise rotation for the left molecule, then you have to predict a counterclockwise rotation for the right molecule or the right bond. And because torsion angles are defined with a cross product, this actually inverts the sign of the torsion angle and also inverts the sign of the correction that you have to predict to the torsion angle. Next slide. All right, so now that we have the requirements for our score model, what does the score model look like? As I have alluded to, this is built using the formulation of equivariant SE3 equivariant convolutional neural networks as developed by Ted Smith, Nate Thomas, and Mario Geiger. Essentially, the idea at a very high level is we have 4 message passing layers, which produce learned feature embeddings for each of the atoms in the atomic graph. Recall that for the input to the score model, we're treating the conformer in Euclidean space. So this molecular graph embedded in Euclidean space is exactly what the model sees. At the end of these 4 interaction layers, we've learned embeddings for each of the atoms of rotation orders up to 2. So you can think of the first order, or rather the 0th order, as scalars and pseudoscalars. The second order, the first order as vectors and pseudovectors. And above that, you can think of those as 5-dimensional irreducible representations of SO3, which is analogous to the scalar and vector case, but just higher in dimensionality. The final layer of the model is what we call a pseudotorque layer. And the job of this layer is to predict a pseudoscalar value for each of the rotatable bonds from the learned atomic embeddings of the neighbors of that bond. And the way that this is done is a three-way tensor product, which differs from the normal tensor product convolution in that the filter for the convolution is no longer just the spherical harmonics, but also the spherical harmonic, but rather the spherical harmonics, the product of the spherical harmonics with a representation of the bond axis itself, which is shown in blue. And the reason why this is necessary is because otherwise the filter has no notion of the orientation of the bond, which is necessary in order to predict a torsional score around the bond. The reason it's called a pseudotorque layer is that this computation is actually conceptually similar to how you would compute a torque if you had force factors at each neighboring atom. And that's shown at right here. You essentially have a three-way product, which you can think of as actually one of the components of the three-way tensor product. So it's just, the normal torque computation is just a little bit of a less exotic version than the full tensor product between these 3 quantities.
So
is the blue Y, is that are you squaring the TP? Are you doing a TP with itself, or are you indexing this with a 2?
Sorry, the blue Y is saying it's a second order spherical harmonic representation. And the reason that this is done,
L equals 2.
Yes, and L equals 2, yeah. And the reason this is done is because we don't want to choose a direction for the bond, because that would be an arbitrary choice.
Why do you, but the L equals 2 has a direction, right? Like
L equals 2 is an even order representation, so it doesn't have a
you don't want to choose a parity. Got it.
Yeah,
Okay.
Yes. Sorry, a parity. Yes, not orientation.
You first
we have a orientation of the axis, but we don't need to put an arrow on the axis.
Got it. So you're first doing the first TP. So that would be, for example, a 2, 1, 1, and then you're going to a 0, 0, like a pseudo-scalar output with the second TP.
Yes.
Got it. Thank you.
Okay, so Bowen, again, why are we doing this?
Oh, yes. So, I mean, we're doing this because we need to provide the some information about the bond to the filter. Because the way that these filters are constructed, there's no opportunity for messages from different neighboring atoms to interact with each other, right? So even if we labeled which atoms are bonded, that form the actual bond that we're trying to compute the score around, there's no opportunity for incoming messages from other atoms, for example, the ones that have black arrows labeled here. There's no opportunity for that information to interact with the information about the bond itself. And so the only way to make that happen is to provide the information into the filter, which is what is done here.
Okay, and have you also tried like just using EGNN, get some node representations, aggregate all of them, predict your torsion angle?
Yeah, so one thing we tried pretty early on is instead of using these tensor product-based networks, we would just use EGNN to produce force vectors or pseudo force vectors, if you will, at each atom, and then compute the torque directly. This does not work. Maybe we didn't try hard enough. Maybe we didn't tune the right things. But compared to the first pass attempt with these tensor product-based networks, it was clear that this was the way to go.
So
sorry, go ahead, Hannes.
This does not work means that it really does not work at all, or that it's just a bit worse?
Oh, it works, but the performance is quite a bit worse.
I think in the last iteration, the last time we tried it, it was actually not learning almost anything. So the loss of the score was basically the baseline loss.
Is it because of this special setup that you have here, or is it because you're including L equals 2? And like, did you ever run your current model with L equals 1 is my question.
Okay.
Yes. Oh, I see what you mean. Yes, we did. And we did do ablation experiments that we can show later on. If you run with L equals 1, there is a pretty significant performance drop. Okay. I do want to note, however, that even if you run with L equals 1, the operation is still not really the same as EGNN.
Right.
For example, you don't get cross products in EGNN. So it's not the same kind of network. And
yeah, of course.
Yeah.
But my question was, is it the L equals 2, or is it the sense that you need the cross product, right? Because without the cross product, how are you going to get the 0, 0, right? You need to.
You do. Yeah. So it's true that you can construct a network with only L equals 1. Well, except for this last step where you have to use L equals 2. Like you can use L equals 1 all the way in the first 4 interaction layers. And it does do worse. So to answer the question, the L equals 2 representation all the way through, it does help. It does help quite a bit.
Cool. Thanks.
Right. Next slide.
Okay. So I'm gonna quickly give an overview of what we talked so far. Is basically I'm gonna repeat many of the things that Hannes recapped. So for training, we start from so we sample. We go through all our training set of molecules. We choose a conformer at random, and then we sample according to the distribution that Bowen presented, a random perturbation at the right noise scale for every torsion angle.
Yep. Oh, so, and this is from just every single torsion or every single rotatable bond just sampled from a uniform?
No, so this is for training. So for training, you need to use the RAP normal distribution. And, you know, at increasing level, this converges, increasing level of noise, this converges to the uniform, which we're going to use at inference time. But when you're training, this is the RAP normal distribution. And so we sample this perturbation and we apply it using, you know, rotations in 3D to the conformer. And so we obtain this perturbed conformer, which we feed into our score model. And then based on the prediction of our score model, we update its parameters and so train as a very similar way that you train a normal diffusion generative model, our score model. And so at inference time, instead, we start from a conformer from RDKit in order to get our local structures. But in order to get, you know, local structures with random torsion angles, we sample a perturbation for every torsion angle, and this perturbation is going to be uniform over the torus, and so we apply it to every torsion angle, and so we are left with a conformer which has exactly the same local structure as RDKit, but has random torsion angles. And so now we are ready to repeatedly apply our reverse diffusion process, whether for each conformation, we compute the score, we scale the score by the right amount, and we add some noise at every step, and then we apply this update. And we repeat this 20 times to get our final prediction. Okay, sorry.
Question. Is it a model, diffusion model, aware of the position of the atoms or this information?
So as Bowen was mentioning before, we use this what we call kind of extrinsic-to-intrinsic torsion score model. So basically the input to the model is the current position of the atoms in 3D, and it predicts this score, so this kind of update over torsion angles. And I also saw a question on the chat, which asks, so do steric clash matter? And, you know, steric clash, you know, can happen in the diffusion because, you know, torsion restricting to the diffusion torsion angles doesn't prevent any steric clash. But critically, unlike models like GeoMol, since our model operates with an input of the 3D space, you know, it can very easily detect a steric clash because, you know, things that shouldn't be this close in 3D space are this close. And so our model actually does much better with steric clashes than many of the previous methods.
Thank you.
Perfect. And so as Bowen mentioned before, so we have this distributional shift problem caused by the fact that during training, our model sees ground truth local structures. By inference time, we use RDKit local structures. Now, we've said that these two are pretty similar, but actually they have some small differences, and these differences actually cause the model that if the model is trained on ground truth local structure to not perform very well when it's fed in RDKit local structures. And so we introduce this procedure and algorithm that we call conformer matching, where as a pre-processing step, so for our training conformers, we use RDKit to get some local structures. So practically, you know, let's say that we have a molecule with 10 conformers, and we sample RDKit for 10 conformers. We do matching of these conformers in a particular way, and I'm not going to go into the details. I'm going to refer you to the paper for this. But once we do the matching, so we are left with a ground truth conformer and an RDKit conformer. Basically, what we do is use differential evolution to match the RDKit, to change the torsion angles of the RDKit conformer to match as closely as possible in 3D the ground truth conformer. So here, in green is a ground truth conformer, and in light blue there is a RD-kit conformer that has been sort of like evolved using this optimized using this differential evolution procedure to be as closely as possible in 3D space to the ground truth conformer, and so you can see they are not perfectly the same because it's they have different local structures, but they are very similar. And this also, these experiments that we did on this and we added to the appendix of our paper kind of also were what I was referring to when talking about how close are the RD-kit local structure to the ground truth one. Okay, so this was the last kind of like component of our method. And so now we can actually delve into the experiments. And so the first...
I have a quick question regarding the previous slide. So you're mentioning that you're using this conformer matching from RD-kit with the conformer from RD-kit. So does that mean that you don't use a random noise to perturbate the model? You only use this differential matching, or do you use both?
No, sorry. I think I maybe I wasn't too clear. So basically, so you do this conformer matching to basically get what you're going to treat as new ground truth structures for your training. And then you're still going to do the same process of perturbing these ground truth, quote unquote, structures and figuring out what's the right score to get back to the right conformer and so all this process. So it's basically the same process that I was describing before, but with the difference that we do this pre-processing that substitutes for training the ground truth local structures with these RD-kit matched, they substitute the original conformers with these RD-kit matched conformers.
So
okay, I see.
Yeah, the problem is, right, we have our ground truth training data, our ground truth 3D structures. But if we were to use them during training, their local structures, then yeah, we could train our model nicely, but then during inference, we always only have the RD-kit local structures. And then, yeah, this is a little bit of a problem. So what they do instead, I think, is to just also during training use the RD-kit local structures, but with the torsion angles changed in such a way that they match the ground truth, our molecular dynamics simulated ground truth training data as closely as possible.
So you technically never learn to mimic the DFT simulation. You learn to mimic how a RD-kit conformer where all its torsion angles are ideal will look like, right?
Yeah, I mean, obviously, you know, our diffusion, I guess you can see in two ways. One is that since we restrict the space over which we operate torsion angles, we are never going to be able, like, if RD-kit if the local structure is not accurate, we can only go so far. And similarly, another way of seeing this is that the way, since our method, you can think of, you know, this local structure, the sort of constraint or input to our score model, you know, our score model basically, and, you know, different methods to compute the local structure might have different characteristics. And our method becomes sort of like, from a sort of like machine learning standpoint, you know, kind of like does not generalize across different local structures. This is something that we have seen empirically.
Can I jump in a little about the comment on this? Yeah, so one very interesting phenomenon that I think, you know, people might find surprising, at least I found it completely shocking when we first tried without conformer matching. We found that the given ground truth local structures, the model is able to recover the ground truth conformer, the entire conformer, up to an RMSD of less than 0.2 angstroms. So this suggests very strongly that the tiny perturbations in local structure, even though we've been saying that the perturbations and the variations among local structure is very small, the information contained in those is actually sufficient to reconstruct the entire conformer. So yeah, that was just something that we found really fascinating and interesting. And of course, when you apply the model to RDKit local structures naively, it just completely fails to predict anything at all. So yeah, just an interesting observation.
And they also have ablations in the appendix where they don't do this conformal matching, and there it's really much worse, like 50% worse performance or something. Yeah.
Also, another point here, like maybe this is more relevant for the next slides where you show the results, but what if you start from random torsion angles? Like you take the ring structure from RDKit, which is always flat, I believe, and you take the angles from RDKit, the bond distance from RDKit, but you start with completely random torsion angles. Do you know if like this would work? Like, will the error be higher? Will it take more steps to converge? Like, what's the difference?
Sorry, Dom, I think it was a misunderstanding because we actually do. So this is a critical part. So is basically this step 2 in our inference procedure. So we start from the RDKit, but then we don't want RDKit torsion angles, so we completely randomize them. And I mean, you could start from RDKit torsion angles, but the problem is that then you would actually have a worse recall because you're basically not really sampling from the distribution which you train.
Yeah, you basically have more chances of getting stuck in a local minima, I believe, if you do that.
Yeah, and also, okay, the distribution that you converge to, it's not the kind of like the full one, but might be just some particular minima.
Yeah, no, okay, so I think it's clearer now. I thought you were starting directly from the RDKit conformer. Okay, it makes sense to start from, to only keep the angles and the bonds from RDKit. Thank you.
Cool, so we get actually into the experiment. So we're looking at an ensemble RMSD, which is basically the distance between the conformers that we generate and the ground truth ones. This is, the classical evaluation that is done in conformer generation machine learning methods. We use geon drugs, which is one of the biggest and one of the most used benchmarks for molecular conformer generation. It has about 300,000 drug-like molecules with, I think, on average, 100 conformers per molecule. And so we compare with state-of-the-art methods. So we have RDKit, which is open source tool that by far, I think, the most used method. Then we have Omega, which is state-of-the-art commercial software, also used a lot. And then we have 2 machine learning recent methods that perform state-of-the-art. So GeoMol from Octavian and Lucky at NeurIPS last year, and GeoDiff from Minkai, Xu et al. At iClear. So this GeoMol is sort of like more similar in its method to the cheminformatics approaches of RDKit and Omega. This GeoDiff, as I mentioned, is an Euclidean diffusion approach. And so you can see that, so we are evaluating precision and recall, and this is what's called the average minimum RMSD. So for precision, so you have, let's say that you have a molecule with 10 conformers. For each of these methods, you generate 20 conformers. And then the precision is looking, okay, if I take one of the conformers that I generate, what's the distance to the closest conformers in the ground truth set? And recall is the other way around. So it's kind of looking how many of the modes, conformers, does my set actually cover? And so as you can see, our model reduces the error of state of the art by about 30% on recall and 16% on the precision, and is actually the first machine learning method to outperform state-of-the-art cheminformatics methods like Omega. And critically, when we compare it to GeoDiff, which is the other diffusion-based method, not only we perform significantly better, but also we only require 20 inference steps compared to the 5,000 inference step the GeoDiff takes to get these competitive results. And this is critical because I think for a CPU, for a single conformer on CPU, it goes from taking 5 minutes per conformer to about like a couple of seconds. So in many applications, this is a critical speed up. Now, another set of experiments that we do, and I'm going to quickly touch on as we are running a bit out of time, is the ensemble properties. So we basically use these methods to generate a set of conformers, and then we test to see if we compute some molecular properties on these conformers, how closely do they resemble the ones computed from the ground truth crest ensemble. And so we use a relatively common technique in the field. So we relax these conformers with XTB, and then we compute properties like energy, dipole moment, homolumo gap, and minimum energy for these ensembles. And so you can see on the right that torsional diffusion, the kind of like conformers generated with torsional diffusion perform like similarly or significantly better in case, for example, of energy to when as compared to the other methods that we compare to. And so this is potentially very interesting, and we are also further exploring this approach with some commercial industry partners. Yes, Tom?
Compared to some of these methods, or mostly like GeoDiff, GeoDiff is able to also modify the angles and the bond length, whether you only move with the torsion angles. Have you looked whether GeoDiff actually predicts better the bond angles and the bond lengths than RDKit, or it's also like mostly working on the torsion, but like it's mostly getting more accuracy thanks to the torsion?
So that's a good question. We actually haven't looked at this with GeoDiff, also because it's quite slow to run, but we have looked at this for GeoMol. So using basically, instead of RDKit local structures, using GeoMol local structures. And I think GeoMol local structures are a bit better, but the difference is actually not very significant in the kind of matching experiments that I was telling you before. So I think RDKit was performing like zero, like the closest, the distance between the closest adaptation of torsion angles for RDKit was like 0.32 Armstrong. And I think for GeoMol was like 0.28. So kind of like quite not very significant. So kind of the difference between RDKit and GeoMol actually is in the torsion angles also. Okay, that's interesting to know. Also, something that's very important when we do conformational generation, and that's worth mentioning, is that it's not simply about generating all the distribution of conformers. The most important thing is the conformers that have the highest probability of being available within like at room temperature in water, right? And this is really proportional to the exponential of the negative energy. It's known as the Boltzmann distribution. For machine learning researchers, this is kind of doing the softmax of the conformers to get like which one, what's the probability of each conformer being present. And here having a lower energy, like an energy of 0.13 as the error to the minimum energy compared to the others, an improvement of 3-fold compared to GeoMol and GeoDiff. This necessarily means that you are much closer
at finding the global minima in the Boltzmann distribution, which is at finding the conformer with the highest probability of actually being there. So I think this is very, very important there, because this is what really matters. You can generate 90% of the conformers that the Crest software gave you. If you don't generate the low energy one, it's really not worth it. So just a follow-up question on that, like, have you looked explicitly at whether you find the low energy conformers like most of the time or not?
Bowen, do you want to take this, or I can take it?
Yeah, so in terms of identifying whether or not we recover those conformers with some more stringent energy cutoff, that is something that we're thinking about doing. We think it would be a very useful evaluation, especially for the industry partners that we referred to earlier. For now, the best evaluation that we can show is the E-min difference that we're showing here. One interesting thing that we think is worth noting is that even though one often cares about the low energy conformers, there could still be merit to training to generate the set of all of the conformers that Crest returns, which has a much higher cutoff of 6 kcals per mole. Now, in practice, a conformer that's that high energy is probably not very useful. But the benefit is that if you do this, then the model doesn't have to, it only has to learn what are the likely areas of the lowest energy conformer, and it can simply sample all of those. It could actually be much harder for a model to learn if it were trained specifically to sample the lowest energy conformers. So we think that probably somewhere in between the two extremes, one having a 6 kcal per mole cutoff and a 0 kcal per mole cutoff for recovering the global minimum, we think that there's probably a sweet spot in the middle where the model is able to, it has enough to learn on, like enough conformers to learn on, but at the same time, it maximizes the expected usefulness of a conformer that it generates. And that's something that we think could be very worth exploring in future work.
Yeah, definitely. And generating the higher energy conformer can still be useful as long as you know that it's a higher energy conformer. Because then if you find that this conformer has very interesting properties, for example, binding at a protein, then one thing you can do to this molecule is to add maybe 1 or 2 bonds or 1 or 2 atoms to the molecule to make it more rigid in that specific conformer. So it's definitely very important to find the whole distribution of conformers, but as long as you know their ranking, as long as you know which one is more important, I think it's fine to recover the larger space.
Yeah, I think this is a great point. I think one of the issues that we kind of went with what's already done in the literature is the evaluation criteria, especially in the Ensemble RMSD, are not Boltzmann weighted, which for some settings might make more sense. We in the end we went with the same evaluation that's currently used in the literature, but yeah, it could, for many real world chemistry applications, might make more sense to use the other type of evaluation. Okay, so with this, I'm gonna give the floor back to Bowen, who's gonna introduce the last part of our method.
May I ask a quick question?
Of course.
You use the diffusion model. So is it correct that the dimension is not too high? And so how relevant is to use a diffusion model and not a direct prediction multi-layer?
Yeah, that's a great question. So this is kind of like very similar approach. So the direct prediction of the torsion angles is a very similar approach to what GeoMold takes. And so I guess, obviously, it is a lower dimensional space, but it's a highly non-independent, I think, space. Because, for example, even just once you, especially once you start to have, more complex molecules with tens of torsion angles. Now, even just predicting steric clashes just from the graph itself, which is kind of what geomol does, is actually quite hard. So for example, if you look at geomol, you often, as the conformance they generates, actually have steric clashes. And so being able to use these diffusion models to learn this relatively complex distribution over the torsion angles, and being able to sample from it, because at the end of the day, it's not just a direct prediction, but is a distribution that you want to sample. We found it to be quite important. So, and in particular, I think we also have in the paper kind of like some experiments on reducing the number of steps that we do, which kind of like goes all the way to kind of like direct prediction, and we see these 10 to 20 steps being kind of the sweet spots, which kind of like is showing that there is a value in the refinement, but it's a much smoother and lower dimensional space, so we don't need to do 5,000 steps.
And the last two questions. So you train using RDKit as a supervised signal. How do you explain the difference in performance?
Sorry. Yeah, sorry. Just to follow up quickly, we don't use RDKit as training signal. We use RDKit local structure adapted to the ground truth conformers. So RDKit, if you look at the distance between RDKit local structures and RDKit's conformers and the ground truth, it's 1.5 Armstrong. If we train with RDKit, we would not get anywhere close.
Okay. Thank you. Thank
you. We is this adaptation in 3D space to the ground truth, which makes these conformers not really look like in terms of global shapes the original ones from RDKit, but very, very close to the ground truth one, with just the difference being the local structure.
The follow-up question is related. So do you think this torsion angle are the most critical, or is the structure, so is the structure easier to predict than the torsion, or is more like it's a combined, so you use the strength of the, for example, RDKit to infer the structure, and then you complete with the torsion?
I mean, I think, and there's definitely much more, a lot of chemistry literature on this. But I think for sure, and for the experiments that we've seen, torsion angles are one of probably the most critical component. Bond length and angles, which RDKit is very good at doing it, but so is Omega, so is geomol, because they are very simple predictions. You just need to look at basically the atom type, and then you have very, very little flexibility. So I think, yeah, the complexity of conformer generation lies on a large part in having the right torsion angles. I think that is a fair statement. Bowen, if you think that's a too strong statement, you can correct me.
Yeah, it sounds,
thank you for the answer.
Correct.
I would like to add something very important on the question about like why using diffusion model instead of direct prediction. And I would like to say that diffusion models will look a lot more like how a molecule would move dynamically in space, and each step of the diffusion model is equivalent to solving one step of a differential equation. And the further away the molecule is from the ground truth, the bigger the push it will get. So suppose you have the energy landscape like that, and you're trying to reach the minimum. The diffusion model will do big steps as it's far from the minimum, and then refine its steps smaller and smaller and smaller. So diffusion model, in some sense, they are much, much better at modeling physical interaction, physical movement, and force fields and energies of molecules than directly trying to predict what's there, right? It's much easier. For example, you're predicting the movements of planet. It's not like if we ask you to predict where planet Earth will be in 2 years, 7 days. Well, it's better to to look at the movement of the planet every day until you get like its position after 2 years, right? It's much easier to do that than just like trying to predict accurately where it will be. And the same holds for a molecule, but there's a lot more degrees of freedom there.
Thank you. Very nice insight.
Okay, Bowen, the floor is yours.
Okay, all right. I'll try to be very quick about this since we seem to.
Bowen, do you have some time constraints?
Oh, no. I
Okay.
don't know how long these things usually go. I know it's been going on for a while.
We don't.
Oh, okay. Well, even so, I'll try to, be concise. Since that's usually a good thing. Right. So our final evaluation is something involving the fact that our model, since we have formulated it using the score-based modeling framework of Song et al., we are actually able to get exact likelihoods from the generative model. And this is done using the probability flow ODE that is defined by the score function. And you can think of this as a continuous normalizing flow that maps from the prior to the data distribution. And so with that setting the stage, what we then need to do is, well, first we want to explore what can we do with the fact that we can have these likelihoods. And as will be shown in a further slide, what we're going to do is we're going to build a Boltzmann generator. And to build a Boltzmann generator, however, you need to be able to speak in terms of a probability distribution over the same space. And the Boltzmann distribution is a density defined over Euclidean space. Whereas our generative model, since it operates on the torus, we get a likelihood on toroidal space. And so first we have to derive a conversion factor that tells us the probability distribution in Euclidean space, a conditional distribution in Euclidean space, based on the density of the torus. And I won't go through the details of this derivation, but you can refer to the paper.
So is this like a change of variable conversion factor?
Yes, it can thought of it as being that way, with the additional complication that we have we have 3 additional degrees of freedom that we have to integrate out. So once we have the Jacobian, essentially we still have to integrate out the 3 degrees of freedom that correspond to orientation. And so that's where the 8 pi squared factor comes from. But otherwise, yes, this is not so different from the regular Jacobian term that you have in a normal flow-based model.
Okay. And now you say, let's build a Boltzmann generator. I don't know if you say a lot about that in the next.
Okay, sure. So Boltzmann generators, at least from a machine learning point of view, they can be thought of as models, generative models, that are trained to match, instead of samples from a data distribution, they're trained to match a energy function or a unnormalized log density, if you will. And so this is of great importance in physical science because the distribution of the ensembles of configurations of molecular systems is in fact defined by the energy as the negative log likelihood. So huge amounts of literature are dedicated to sampling from this distribution. And Boltzmann generators are just they're an innovation for training machine learning models to do so directly. So yeah, so that's kind of what a Boltzmann generator is. To put it very simply, it's training with an energy function rather than with data. So in order to do something like that, you need to have access to the likelihood. And the way that we do so here is actually, to our knowledge, a novel way of doing it, because we have a score-based model that we can occasionally use as a flow if we need to generate something with known model density. But at the end of the day, it still is a score-based model. And so this gives rise to a very interesting training procedure that consists of 2 stages. In the first stage, we aim to simulate data samples from the Boltzmann distribution. And the way that we can do this is by using the model as an importance sampler for the Boltzmann distribution. This is the part where we use the model density. We use the model density along with the ground truth energy function to reweight the samples such that they approximate the Boltzmann distribution. It's important to note that no gradient descent is performed during this stage. The gradient descent and the actual parameter updates happen in the score matching stage, where we use the simulated samples from the Boltzmann distribution with the normal way of training a score model with the score matching loss. And as the training proceeds, and as the model learns the score, it improves as an important sampler. And the really interesting thing about this, and the key difference with the existing energy-based training methods, is that the model density is not used to update the weights. The model density is only used in the resampling stage in order to reweight the samples that are drawn. So, this contrasts with existing Boltzmann generators, which are based on flows. And the loss function for the energy-based loss function for a flow in that case actually directly tries to match the model density with the target density. Here, we don't do that, and we just use the normal score matching loss, except with simulated samples from the Boltzmann distribution. And it's only in simulating those samples that we use the model density. Next slide. Oh, sorry. Any questions?
Does training like this change the sample quality?
By sample quality, are you referring to, for example, the Ensemble RMSD and so on and so forth?
Exactly.
Yeah, so it's actually a completely different setting. So here what we're doing is we're training a model to match the conditional Boltzmann distribution. And we're trying to draw independent samples from the conditional Boltzmann distribution. In the conformer generation task, well, the way that the task is framed is actually trying to generate the local minima of the Boltzmann distribution. And it's also unconditional. So, in the former setting, which we've devoted most of the paper to, we're trying to generate the local minima of a unconditional Boltzmann distribution. Whereas here, we're trying to generate independent samples from a conditional Boltzmann distribution. So it's really quite different. Further difference arises from the fact that in this energy-based training, for computational feasibility, we train using the MMFF energy, which is a classical force field. So that is a very different energy function than what is used to optimize the conformers in our training set. So it's really so different of a task that it doesn't make sense to compare the two.
Okay. I don't claim understanding, but let's go.
Okay. Yeah. All right.
So may I maybe make a question? So
Okay.
do I understand correctly that you use the Boltzmann to sample, and the Boltzmann energy is the probability that you train using gradient descent?
Yes. So we're training the model to match the Boltzmann density. Yeah. I'm sorry. Maybe I didn't understand your question.
And yeah, but the Boltzmann energy is your probability which you're training. So or I missed something.
Yeah, so the model gradually kind of learns to resemble this Boltzmann energy, but we don't claim, especially at the beginning, this resampling critically is using important sampling because our probability distribution of our model is not, especially at the start, even close to the true energy function, to the one given by the true energy function. So we use important sampling to reweight in a way. So this resampling actually generates sample. It's an important sample, so it doesn't actually generate samples, but it generates samples from the ground truth Boltzmann distribution, at least the ground truth given by the energy function. So the model in this part, the model distribution is actually just used to basically rescale these importance weights. Does that answer the question?
I'm not sure I understand. Where do you get the energy function for the Boltzmann?
Yeah, okay, sorry. I think I realized the necessary clarification. So when we refer to the Boltzmann density and the energy function here, we're referring to the Boltzmann density induced by some ground truth energy function. So in our experiments, we use the Merck molecular force field. You could, of course, use any other energy function. But the objective of this training is to have the model match the Boltzmann density that is induced by that external energy function. So when we say Boltzmann distribution, we always refer to that external distribution. We never refer to our model density as a Boltzmann density.
Okay, thank you.
Okay, so here are some results for experiments with the Boltzmann generator, which we call the torsional Boltzmann generator, since it only samples torsion angles. So the way that we do this evaluation is after training the model with the energy-based training shown on the previous slide, we generate 32 samples for a specific local structure on an unseen molecule from the test set. Right, so this is actually one point that I do want to highlight, which is that traditionally Boltzmann generators have operated on, for example, if you look at the original Boltzmann generator paper, it prominently features intrinsic coordinates. And so it learns a generative model over intrinsic coordinates directly. It learns transformations of those coordinates. But because an intrinsic coordinate system is specific to a given molecule, you actually have to train a separate model for every molecule that you would hope to generate the Boltzmann distribution for. Our extrinsic to intrinsic score modeling framework allows our model, for the previous tasks as well. It's actually very necessary for conformer generation that it generalizes to different molecular graphs. And this is a property that the torsional Boltzmann generator also inherits. So the way that the evaluation is done is we generate 32 samples with the trained model for an unseen molecular graph with a particular fixed local structure. And we compute the importance weights of those samples out of 32, since we generate 32 samples. And if the model is able to match the Boltzmann density perfectly, then you would get 32 samples, an effective sample size of 32 if you draw 32 samples. As you can see, we're not quite there yet. We're not, it's not a perfect Boltzmann generator, but it's important to compare with a reasonable baseline. So a reasonable baseline could be some MCMC-based technique. So what we implement is we implement an annealed importance sampler baseline. And for the annealed importance sampler baseline, we tune the parameters of the transition kernels to try to make it a good baseline, a reasonable baseline. And for each of these two approaches, our model and the annealed importance sampling baseline, we generate samples with different numbers of steps. So for our model, this would simply mean denoising steps. For annealed importance samplers, this would be the number of intermediate annealing distributions. And what you can see here is that the annealed importance sampler for 5 steps or even 20 steps, for the most part, you have an effective sample size of 1, which means that based on the model and the Boltzmann weights, almost all of the statistical weight of the 32 samples that you have comes from just 1 sample. So that's not a very good generator at all. Our model does much better with 5 steps, and especially with 20 steps, where we have effective sample size of 6. And notably, the annealed importance sampler, the tuned sampler, is unable to achieve this level of performance even with 100 steps. Here we're showing results for 500 Kelvin. We also have results for other temperatures that you can look at in the appendix. Okay, wow, that was the last slide. Right, okay, so to conclude, the overall paradigm that we have tried to push for in this work is that because the flexibility of a molecule lies in torsion angles, the difficulty of conformer generation also lies in torsion angles. And so machine learning methods should focus on generative modeling over this torsional space. And we find that if we do so and apply it to the framework of diffusion-based models, we get significant reduction in dimensionality, which makes the learning task much easier and much faster in the sampling process. Using these conceptual advantages, we find that we get results that, for the first time, allow machine learning models to exceed the very best cheminformatics-based baselines, such as omega. And we find that the additional theoretical property that comes from using score-based models allows us to have a new way of training a generalizable Boltzmann generator. The archive paper has much more details, and feel free to play around with the code. And thank you all very much for listening, and we're happy to take any questions anytime.
I suppose I have one. So first of all, thank you both for the presentation and very amazing work. So the last part of the likelihood, so you're using the Boltzmann a generator in order to generate the samples. But in theory, the diffusion model is also a way to model distribution. Do you think you can use the model itself? So you can use the diffusion model to generate the sample, or there is something I'm missing?
Yes, okay. So I think there are two things. First of all, if you try to use the model trained on the normal training set, that training set consists nearly entirely, well, I mean, by design, it contains the local minima. So the induced distribution that you get from that model density is sharply peaked around the local minima of every energy basin, since the model has it's able to pick up roughly speaking where the minima of an energy basin is. That's why it's getting pretty good RMSDs, and so that actually fails spectacularly to sample independently from the Boltzmann distribution. So if you want a Boltzmann generator, it's actually very important to train, not on only the local minima, because that will not work. The second thing is, if I follow correctly the exposition of diffusion-based models for physical and chemical settings that you explained earlier, I think it might not be completely correct to say that there's a natural connection between diffusion-based models and the energy function. In fact, strictly speaking, the energy function has no role at all in the formulation of diffusion-based models, and adding noise to the data distribution is not the same as increasing the temperature of the Boltzmann distribution. So I think the formulations are sufficiently different that at least at the present moment, maybe there are more theoretical developments that I'm not aware of, but at least at the present moment, I don't think one can say that diffusion-based models are, more well suited for molecules than they are for other kinds of data modalities. I could be wrong on this if there's additional theory that I'm not aware of, but that's my current understanding.
Yeah, what I mean is that the diffusion model can, how to say, learn the distribution of the input data, no? So in this sense, but not the energy by itself. So I understand that you use the energy in order to teach the model what to do, so to generalize better, no? For unseen states. Thank you.
Yep, for sure.
Okay, perfect. Then thank you so much for the nice presentation, and thank you much more for the awesome paper. I like it. I love it. But let's have maybe one last very important question. Why is parity in energy only approximately very nearly parity invariant?
Okay. Wow. Okay. Well, I'm sure there are actual physicists in the audience who could give a much better exposition than I could. But the fascinating story behind this is that, for very many decades, at least prior to the 1960s and 70s, charge parity and time were thought to be, very fundamental conservations of nature. And by this, what I mean is that if you invert any of these coordinates, the form of the physical laws of the universe do not change. And so this holy trinity of CPT symmetry was believed for quite a long time, since it definitely seemed the case to everyone. And so one of the implications of this is that there is no unambiguous way to define, for example, a left-handed or a right-handed coordinate system. Let's say that you were communicating with some civilization outside of our own, and you were trying to communicate with them what you meant by left. If you think about this a little bit and you imagine that you can't just point to something and say, oh, this direction is left, how would you actually do something like this? Well, if CPT symmetry is held, then it's actually not possible to do this, right? It is impossible to distinguish our universe from a mirror universe, and this was believed for a very long time. But in the 1960s, I believe, at Columbia, there was an experiment that was done that showed that one of the four fundamental forces of nature, the weak force, actually does not obey this at all. And so, it was very hard for the community to believe for a very long time, but it turns out to be true. And so that is what we refer to, the fact that the weak force, since it does not respect parity symmetry, it is actually possible to have an objective way of defining what a left-handed or a right-handed coordinate system is.
Okay.
And it is also possible to distinguish a conformer from its mirror image, because the weak force, the interactions, will induce a very, very tiny energy difference. But it's so small that we ignore it. Yeah, sorry, go ahead.
Like, what's two different things do I need to see this different? Like, we have can an atom have the quarks in different positions, or yeah?
I am not a physicist by any means, but if I understand correctly, interactions among quarks, that is with the strong force and not the weak force. So I think that's probably still okay. Yeah, so to see this difference, you would need to have an interaction governed by the weak force and set things up in a particular way. I am very much not a physicist, so I will just shut myself up right here. Oh yes, thank you, Alexandra. Alexandra says you need decays of B mesons to distinguish it.
Okay, that tells me much more. That's perfect. I think the ideal position to, or the ideal point to end it. And then, yeah, thank you, Bowen. Thank you, everyone else in the audience, for the awesome comments, the awesome questions. And yeah, for example, Simon, the other Simon, the third Simon, and also Alex, Dom, and everyone else.
Yeah, I'm sorry if we missed some of the comments in the chat. For any questions or like anything, problems with the code and anything else, feel free to reach out to us by email, and we'd be happy to respond.
Thanks a lot for the great presentation. Like I've read your work many times, even though it was available yesterday on archive. It was great to have you.
Alrighty, then see you everyone.